So today we're starting with a new chapter, which are nonlinear models. So, sorry, I had an additional monitor plugged in, so there were problems. Nonlinear models. So we start in the same way as we started lecture 1, linear models. We are given a sample of data points. So we are given data points. X1, Y1 up to XM, YM. Those X's are tuples of real numbers, n tuples, and those Y's are just values. So those are real numbers. And we would like to feed those data points with some function. So we are searching for a function f. So this is a function mapping from r to the power of p plus 1 into r. And it's the function which is dependent on those first coordinates of our data point. It's in fact then p plus n. So it maps every data point. And then we also have those parameters, p parameters, into some real number. So this is a function which has n plus p arguments. The first n arguments are our data points, are reserved for our data points, and those other p arguments are our parameters. So parameters. If you recall from linear models, this function f was supposed to be linear in those parameters a1 up to ap. So let me just write this in linear models. F was of the form f of x in the parameters a was of the form a1 times some function phi1 of x plus so on plus ap times phi p of x. So the crucial thing was that this f was linear in a's. And of course, the condition which has to be fulfilled with this function f is our condition is that f of x1 in the parameters a1 up to ap is equal to y1 and so on also for the other points. F of xm in the parameters a1 up to ap is supposed to be ym. So in the linear model situation, this system I've just written transformed into matricial form. So our vector of unknowns was a1 up to ap. Those coefficients phi1x up to phi px were the rows of the matrix A. And those y's were the right-hand side of the system, were the vector B. So in linear models, we had ax equals to b. And we studied for the last 3 weeks, we studied how to solve such a system. and we separated few possibilities. So one possibility was that this system is solvable. Then the other is that the system is not solvable. And then we also separated the cases where we have less rows than columns, so less constraints than unknowns, and the possibility that we have more rows than columns, so more constraints than unknowns. But now we are generalizing this situation. So now we are allowing more sophisticated functions f. So we also allow transcendental functions in a's, also higher powers of a's and so on. And the system will not be matricial anymore. So it won't be possible to transform the system into a matricial form. So in the nonlinear situation, in the nonlinear model, we allow that f is nonlinear in the parameters a1 up to ap. Now, let's look at some examples which naturally occur in the real life world. So I will just use slides for those three examples. So one example is so-called exponential decay or growth. So in this example, we allow f to be, so this f is a function of two parameters, a and k. X is our first coordinate of the data points, and the function f is of the form a times e to the power of kx. So it's some exponential function. This k determines the slope, and this a determines, so this k determines, this a determines the slope, and this k determines the width of our exponential function. And why is such a model important? So this model is important because it is the solution of this differential equation. So we have some quantity y, which is dependent on some variable x. And this quantity, the rate of change of this quantity, so dy over dx, this measures the rate of change of this quantity, is proportional to the current size of value y. So this k is the proportionality constant. So we have this differential equation which has to be solved, and the solution of this differential equation is exactly exponential function which depends on this k and a. Probably you know how to solve this differential equation already from analysis. So we can use separation of variables. We put dy over y is equal to k times dx, and then we integrate both sides. But even if you don't know how to solve it, don't worry. So we will do it in the third part of this course, when we will deal with dynamical models, and we will repeat how to solve those basic differential equations. So based on this k and a, we have different solutions to this differential equation. So here are some solutions: this red and green and blue and pale blue. Those are the solutions at the different k's. So this is one example of a nonlinear model. Then another example which you already know from statistics. Is so-called Gaussian model. So here, our function is dependent, again, it's a function of 4 variables. The first variable is the first coordinate of our data points. And then we have 3 parameters, a, b, c, to be determined. And the function is a times e to the power of minus, and then we have x minus b over c squared. So for appropriate a, b, and c, this is just the density of the Gaussian distribution, of the normal distribution, and you know it from statistics. So precisely a is 1 over sigma times square root of 2 pi, and then b is mu, and c is square root of 2 sigma. And you get a normal distribution with mu as the expected value and sigma as the standard deviation. But except statistics, this model is also important in other areas such as signal and image processing. So these are few examples of different parameters. So we have here written mu is 0, so expected value is 0, and then sigma squared is 0.2, and we have this blue curve. And at some different parameters, we have different curves. So this is another model which is important in different situations. And there is a slight generalization of the first model. So if you recall above, we had this exponential decay. The rate of change of the population size is proportional to its value. So the higher the population size, if k is bigger than 0, then the growth is higher, and it grows faster and faster. But of course, if you want to model a real life situation, then we have to also take into account saturation of the environment. So at some point, the population won't be able to grow anymore because there won't be enough resources. And to take into account also the saturation of the environment, it's natural to here add some factor into our differential equations. So we would like to say, yeah, the growth is proportional to the size when the population is small enough, but when it's big enough, we would like that this growth stabilizes and then stops. And how would we model this? We can add another factor here. So k times y times, and then a minus y, where a is this saturation constant. A tells us when y will be almost a, then this growth should be slow because a minus y will be then near to 0. And we get so-called logistic model. So it's here. So our differential equation, as I said, we added here 1 minus y over a, or we could also write here a minus y and put this a in front of the parentheses. It has the same meaning. So when y will be almost a, this 1 minus y over a will be almost 0, and the growth will stop. But when y will be small, this factor won't have a lot of influence on this right-hand side, because 1 minus y over a will be almost 1. And it turns out that the solution of this equation, differential equation, is this one, a over 1 plus b e to the power of minus kx. And this is called a logistic model. And this is the graph of some logistic function. So at the beginning, it's exponential. And when the saturation of the environment is getting close, the growth stabilizes, it becomes linear, and then stops. So those are three models which occur naturally in modeling real life situation. But of course, there could be also other examples which are very specific. Let's look at one of them. So this is a very specific example. We have the situation is that we have a microwave. So, and this microwave is forbidden because its radiation interferes with the radio telescope, which we have somewhere in the area. And then we measure. So, but we know that the intensity of the radiation of the microwave decreases with distance from this microwave according to this law. So we have this microwave, and then we have some point which is at the distance r to the microwave, and the intensity of the radiation of the microwave here in this point is equal to UR is alpha over 1 plus R. So we don't know what's this alpha. This is some constant, but we know that it's inversely proportional to 1 plus R. And then here we have three data. We don't know where the microwave is positioned, but we measured the distance. We measured the radiation at three different locations. So let's say that we have 0, 0, then we have 1, 1, and we have 0, 2. Let's say we have this triangle, and we measured the signals at those positions and got 0.3 in this point, and then 0.27 in this point, and 0.36 at this point. And we don't know where the microwave is positioned. But based on our model, which is this, we know that this 0.3 is equal to alpha over 1 plus R, where R is the distance between this point 0, 2 and the position of the microwave, which is AB. So here AB, let me write more clearly. So AB is the position of the microwave. And then we know that radiation at the distance R is alpha over 1 plus R. And then we have what's the distance between 0, 2 and AB. It's exactly, the distance is exactly, so by Pythagoras theorem, it's a squared plus b minus 2 squared. So this is a squared plus b minus 2 squared, and everything under square root. So this means that 0.3 is equal to alpha over 1 plus square root of a squared plus b minus 2 squared. And then we do the same for the other 2 points. So here we have, again, the distance is by Pythagoras theorem square root of a minus 1 squared plus b minus 1 squared under square root. And so 0.36 must be alpha over 1 plus the distance, which is square root of a minus 1 squared plus b minus 1 squared. And then the same for the third point. So 0.27 is alpha over 1 plus, and then a squared plus b squared. So we have these 3 equations in 3 unknowns. So we needed 3 positions because in this equation there are 3 unknowns. So we will need at least 3 positions to determine those parameters precisely. So if we would be in the 3-dimensional space, then the position would have 3 coordinates x, y, and z, and we would need 4 points. So the signal measured in 4 points, because then 4 parameters would occur in this model. So our task is to solve these 3 equations in 3 parameters. And you can try by yourself to express, to reduce the number of variables, or express one variable with others and try to solve these systems. And you will see that it's impossible to solve it analytically. So it's not possible. So compared to linear systems where you can do elimination of variables to solve the system, here this is not possible. Whenever you have nonlinear equations, it's very difficult to solve it analytically. There are not a lot of systems which could be solved by a formula. And so let's stress this. Such a system is in general not analytically solvable. So analytically, what does analytically means? This means that there doesn't exist a formula to express the unknowns. Even if we are in the situation of one variable and one equation, there doesn't exist formulas to solve every such nonlinear equations. Already, if we are working with a polynomial of degree 5, we cannot solve it analytically. So even if we are solving one equation in one unknown, it is usually not possible to solve. It analytically. polynomial of degree 5 or more, is an example of this fact. So we have, if you have a polynomial of degree 2, then we all know how to express both solutions. We have a formula x1, x2, and we can calculate its roots explicitly. And there are formulas to solve a polynomial of degree 3. They are much more complicated, but they exist. And even more complicated formulas for degree 4 polynomials. However, for a general polynomial of degree 5, there doesn't exist a formula with which we could express all its roots. We cannot even express one of the roots. And here we bounced on this problem. We have a bunch of nonlinear equations. We would like to solve them. However, analytically, this won't be possible. And today we will learn how to solve such a systems. Of course, we won't be able to solve it precisely, but we will try to find approximates of the solutions of such systems using one of the numerical methods to do this. And the numerical method will be Newton's method and its generalizations for rectangular systems, which is called Gauss-Newton method. So we will solve such systems. We will learn how to solve such systems. Approximately by the use of a numerical method which is called Gauss-Newton method. So the plan for today is to come to this Gauss-Newton method. First, we will start with one equation in one known and recall a special case of this Gauss-Newton method, which you probably already know from analysis. This is the tangent method. Then we will generalize this to square systems like this. This is 3 times 3 system. So we have 3 equations and 3 unknowns. And we will see so-called Newton's method. And then finally, when we will have more equations than unknowns, we will generalize this Newton's method to Gauss-Newton's method. Of course, when there will be more equations than unknowns, we cannot expect to get exact solution. Their exact solution probably doesn't even exist. But we will search for the solution by the method of least squares, which you already know from linear models. So this is the plan for today. Are there maybe any questions so far? Okay, if not, let's first, to be able to apply this numerical method, Gauss-Newton method, there will be first some trick, which is very easy. It's just a technical thing. So we would like to transform the system into the system for which we are solving, for which we're searching for its zeros. So we have this system, what to do to transform it into the system such that on the left side there will be only zeros. Yeah, this is easy to do. We just put those values on the right-hand side. And so we get here 0 and minus 0.3. And here we get 0 and minus 0.36. And here we have 0 and minus 0.27. So it will be more convenient for us to not deal with, to numerically solve not system of this form, f of xa is equal to y, but a system of the form f of xa is equal to 0. So what to do? We just introduce new unknown, new functions. So here we have g of x1, a1 up to ap minus y1 is equal to 0. And here we have g, I mean, this is still our f. We just rewrite this system into f of xm, a1 up to ap minus ym is equal to 0. And this is now our g. So this is our g on x1, a1 up to ap. And this is our g on xm, a1 up to ap. And of course, then we have also this ym as a parameter. So y1 is equal to 0. So the first thing is to transform our system into the system for which we are searching for its zeros. So let's just write this separately. So our setting still we have data points x1, y1, xm, ym. Those are data points in Rn times R. So x's are n tuples and y's are real numbers. And we have a function g of x, y, a1 up to ap. This is a function from R to the power of n times R times Rp into real numbers. And we are searching for the zeros of our system. So we are solving g of x1, y1, a1 up to ap is equal to 0 up to g of x1, xm, ym, a1 up to ap is equal to 0. So this is our system. So given, and so the x1 and y1 are given, and xm and ym are given, while a1 up to ap are parameters. So these are unknowns. And so we have how many equations? We got m equations. with p unknowns. So this recall that these x1 and y1 up to xm and ym are given. So unknowns are only parameters a1 up to ap, and we have m equations. And we can denote, so in fact, we can denote this function as, so we can say that this first function is g1. It maps from r to the power of p into r, and it is equal to g1 of a1 up to ap. This is equal to what's written up. So it's capital G of x1, y1, a1 up to ap. And then g2, and so on up to gm, which is again a function of p parameters into r, and gm on the parameters a1 up to ap is equal to capital G of xm, ym, a1 up to ap. And those are called, so g1 up to gm are called coordinate functions of a vector function g. So we form h, which is a function from r to the power of p into r to the power of m. In this h has components g1 up to gm. This h is called a vector function of a vector variable. This vector function refers to the codomain, which is r to the power of m. So it's the codomain of h are vectors, and this vector variable refers to the domain. So the domain is not real numbers, but tuples of real numbers, so vectors. That's why we call h a vector function of a vector variable. And g1 up to gm are called coordinate or also component functions. Coordinate functions. Or component functions. And so in our model, we built those coordinate functions so that we are searching for its zeros. So here, what we are searching for, so our goal is to determine the zero of h. So we are solving h of x is equal to 0. Or to not to confuse you, let's say h of a is equal to 0. So this a is a tuple of unknowns, and this 0 is in fact a tuple of zeros, m of them. So to recap that I don't that I don't lose you, we started with the nonlinear model. This was our function f, which was dependent from x, y, and parameters a1 up to ap. I mean, from x and parameters a1 up to ap. And we said that we want to find parameters a1 up to ap, so that f of xi, a1 up to ap is equal to yi. And this is true for every I, so for every data point. And then we said that it will be more convenient to solve this numerically by putting everything on one side, so that on the right-hand side we have only zeros. That's why we put yi's on the left-hand side. And then we introduced a new function capital G, which was f of x, y1 up to a1 up to ap minus y. So this was our capital G. And then we plug in this capital G, which is written here, all the data points, x1, y1 up to xm, ym. And if the system is solvable, then we should get zeros at some parameters a1 up to ap. So those functions should, those values should all have zeros in some parameters. But notice that the first two coordinates are fixed, so they are not unknown. So the only unknowns are a1 up to ap. That's why those are in fact functions of p parameters, and we write them as g1 up to gm, and collect them in some bigger function, some new function, which is called h. And now this h is really a function from p tuples into m tuples. So p tuples are parameters, m tuples are correspond to each of the data points, so each of the conditions, each of the constraints. And the construction shows us that we are searching for the zero of h, for the vector zero of h.
So is H a matrix?
So when we plug in H some concrete value of A, yeah, this will be matrix. Yeah, we can look. So if this H, what is this H? So H, yeah, we cannot write it in the matricial form. So this H is in fact, we have first coordinate is H1, H2 up to HM. And how do we calculate the value of H in the point A? It is just H1 on A, H2 on A, up to HM on A. So it's not a matrix, so it's a vector of functions. And we calculate each function in the point, and we get a vector of real numbers. So for example, h of a1, a2 is, let's say, a1 squared, 3a1 squared plus 4a2 plus cosine of a1 plus 5. And then the second coordinate is 2a1 plus 5a2 squared plus a to the power of a1. And we can have more coordinates. So a1, a2 plus a1, 5a1 plus tangents of a2. So you see in here, this is G1 of A1, A2. This is G2 of A1, A2. And this is G3 of A1 and A2. So it's not a matrix, so it's a vector function. So every component of H is a function which depends on the parameters A1 and A2. And you could ask, where did X1 and Y1 and so on, XM, YM, disappear here? They're in fact hidden in those coefficients 3, 4, and so on, because so we built these G's, G1, A1 up to AP as capital G of X1, Y1, A1 up to AP. But since X1 and Y1 are known, they are the real numbers. And when we plug them in, the only unknowns which will remain are those A's. So in fact, if this example would really come from some model, then those X's would be hidden in those coefficients 3, 4, and so on. And maybe to see why it's, when we would get the matrix function, yeah, when if the model was linear, then this would be nothing else but the matrix system. So if G1, Gm are linear, we would get a matricial system. For example, I will write one example. So let's say that H of A1, A2 is equal to, and here I will just write three linear equations. So 3A1 plus A2 plus 5, and then A1 plus A2 plus 1, and then A2 plus 7. This could be written in the matricial form. So 3, 1, and then 1, 1, and 0, 1. And the unknown would be A1, A2. And then plus 5, 1, 7. So I collected those 5, 1, 7 into this B. And then those coefficients 3 and here 1 are here. And so here 1, 1 are here. And the last equation was just 0, 1. And in fact, we will see that Gauss-Newton method for solving such a system, such a nonlinear system, is based on the approximation of this system with a linear system, with such a linear system. So if the system is linear, then it can be expressed in this matrix form. However, our system is not linear, but Gauss-Newton method is based on approximating this system with a linear one. And we will see in the second and third hour how to form this linear system. Maybe some other questions?
Yes. Can you go just this a little bit up?
Mm-hmm.
So
More?
here, yes, you have written this that H1 AH2A to HMA.
Yeah.
And then under this G1 from so H1, H2. So what's the difference between H1 and G1?
Okay, yeah. I should write here. I should write here G1 and GM. Yeah, I used a different notation. Yeah, it's the same. G1. I will just write here H1 is equal to G1.
Okay, thank you.
So here I wanted to write a general situation, but in the example I refer to G's above, how we came to this general setting. So yeah, from now on, when we will be in general setting, so we will work with capital F or capital G or capital H, and the coordinate functions will be then F1 up to Fm or G1 up to Gm and so on. We continue with the second hour. So maybe what we did in the first lecture was a little bit confusing. So let's recap shortly our setting. And this is usually the problem where students make mistakes when they use wrong functions in the method. So it's important to understand these transformations we did so that you use appropriate function in your model. So first, we are searching for this fitting function, which is a function in n plus m variables, and it maps into real numbers. So these first n variables are for x's, and those n variables are for the parameters. So I will write this in this form with vectors to shorten the notation. So x vector and a vectorial. So this is a fitting function we choose in our model. So we are given this function in advance. We have to choose it according to a real life model. And then what we form from our data are those equations, f of xi, a vectorial is equal to yi, and this should be true for every I from 1 to m, if m is the number of data points. And from now on, the following 3 steps are only technical so that we can use numerical methods we will learn today. So nothing else, just transformation of the problem into the problem which is appropriate for numerical method, so-called Gauss-Newton method. So what we do is just put everything on one side, f of xy, a vectorial minus yi is equal to 0 for every I. And we introduce new functions. So those are left-hand side functions, which we write as gi. So gi, and the unknowns here are only a's. So gi on the vector a is f of xi, a vectorial minus yi. So we introduce those functions. And condition 3 says that we would like to find a such that all those gi's are equal to 0. So or we introduce function capital H. Also, this is a function from p tuples into, now not into real numbers, but it's vectorial function because we collect all g's, all small g's into H. So we have m. For each constraint, we have one component. And this H is just a function with coordinates, which are those G's. Not P, but M. And what we want, so 2, 3, 4 are all equivalent to searching for A, which is a common zero of all G's, which is just a zero of this H. And again, not to be confused, I can write here zero vectorial, meaning just a vector of zeros. And from now on, everything will be numerical methods. So we transformed our problem into the problem of searching a zero of a vector function H. So from now on, we are working with numerics. So with numerical algorithms for finding zeros of vector valued functions. Of a vector variable. So as I said before, vector valued means that the codomain is more than one-dimensional, and vector variable means that the domain is more than one-dimensional. As we saw in the example above, if all of those G's are linear functions, then H can be expressed in the matricial form. So if G1 up to Gm are linear in A's, then H of A is just some matrix times this vector A of unknowns plus B. I mean, here, if they are linear, then this B is 0, but so if they are linear, then it is just A times A, where A is some matrix, a matrix of numbers. But if they are affine linear, meaning that the constant term doesn't need to be 0, then also H of A can have a non-constant term which is not 0. And this is what we're gonna use. Even if H won't be linear, we will use a linear approximation to solve, to approximate the solution of this system. H of A is equal to 0. So for these linear models, we already know how to solve them. We studied a few techniques for different types of linear systems in the first 3 weeks. And now we already know how to solve them, so we will use this to approximate the solution of a nonlinear function h. So the question is how to choose appropriate matrix A. So what we will do is to approximate H with an appropriate matrix A to find the approximate solution of H of A is equal to 0. So this is the question. But of course, this procedure won't end in one step. It won't be possible to just choose A and do one step of the calculation of A plus B to one step of A plus B is equal to 0 to solve this system. We already know how to solve this system. So it won't be enough to do one approximation and then solve the approximated linear system. And what we will get will be a good approximate of the true solution of H A is equal to 0. So this won't be enough. Some iterative way of doing this will be needed. So this matrix A will change from step to step. So the procedure will not end in one step, but more steps will be needed. And in each step, the matrix A will be different. So in each step, we will need a new, I will put this in the parentheses, matrix A. So matrix A will depend on the approximation for the, so if AR is art iterate in our procedure, then A will be dependent on this iterate. So A will be dependent on the iterate AR. So this is AR means this is the vector in art step of our method. And this vector will then determine what's the next A. Okay, and we will shortly see what's the candidate for A. Let's look at the simple case where we have one equation and only one unknown. So let's look at the special case of this procedure. Special case. And this will give us idea to generalize to higher dimensions. So H is just a function of a univariate function, so it's not a vector function. It's not the variable is not vector variable. It's just a usual function. So H of A is a real number. If we write, if we draw a graph of H, it is something like, let's say it's something like that. Okay. And we would like to find this zero. So we're searching for the zero. So this is our H. And we would like to find the zero. Let's call it alpha. And you all know tangent method to do this. So what we do, we choose some approximation of alpha, let's say x naught. And what we do in the tangent method, so we calculate h of x naught. So we come here. This is h of x naught. And now we would like to linearly approximate our function around this point. So what does this mean? What does this mean? This means that we calculate the tangent to the curve in this point. So we calculate the tangent. And where the tangent meets the x-axis, this is our next iterate. So this is x1. And I will use another color because everything will be too dense otherwise. So this is x1. And what's the formula for this tangent? So formula for this tangent was in the point x naught, we wanted that it is, so let's write L of x. So what was our goal? So in x naught, L of x naught, it should have the same value as our function h. So it was h of x naught. But the slope of this tangent was the same as the derivative of h. So L derivative of x naught was the same as h derivative of x naught. So this requires that we know how to compute the derivative of h. So h must be differentiable, and we should know how to calculate the derivative. These were two conditions, and it turns out that then L of x, the simplest way to express it is L of x naught plus L derivative of x naught times x minus x naught. So this is the easiest way to express this tangent. So if we plug in x naught in this expression, so the second term disappears because we have x naught minus x naught. While if we differentiate this equation, so then this first term disappears and x minus x naught differentiated is just 1. And what remains is this L prime x naught. So this is really the right expression for the tangent. And how to get x1? So x1 was the x value where L of x was equal to 0. So L of x1 was equal to 0. So this is L of x naught plus L prime of x naught x1 minus x naught. If we put everything on one side, we get minus, if we, our unknown is here x1, so we leave x1 on one side and put everything, every other constants on the other side. So we get minus L x naught divided by L derivative of L in x naught and plus x naught. So plus x naught is equal to x1. And I can write this in a clearer way like that. So I only expressed x1 from this equation. And this is another, so this is the new iterate. And recall that, so this L x naught and L prime x naught were in fact h of x naught and h prime of x naught. So x naught minus h of x naught is h prime of x naught. And this is the new iterate. And now I repeat this procedure. In x1, I go to the graph of h. I have here h of x1. Calculate the tangent. And where the tangent meets the x-axis, this is my new iterate, so x2. And if I do all the same calculations, I get that x2 is equal to, so I will use this last expression and just plug, instead of x naught, I will plug in x1. So x2 is x1 minus h of x1 over h prime of x1. And this is basically what the tangent method does. We are repeating this procedure, and I won't draw on in this picture because it will be too dense and nothing will be visible. But you can see that in a few steps, we'll be very close to the real root of our equation h of a is 0. And this is tangent method. So let's write this in the form of an algorithm. So Newton's method, Newton's or tangent method. We have h from R to R. We would like to find h of alpha is equal to 0. And what we do is choose an initial term, an initial approximation. X naught is an initial approximation. And then we are repeating this calculation. So next iterate xr plus 1 is last iterate minus h of xr over h prime xr. We are repeating this until some stopping criteria is met. So there is no guarantee that this Newton's method will converge, but if it converges, then, so if this method converges, then the differences xr plus 1 minus xr, so the absolute values of those differences between the last two iterates will go to 0. But usually, if since we don't know what's the true value of the solution, it could be very small. It's not good to take xr plus 1 minus xr is small enough for the stopping criteria, but it's good to, it's better to calculate the relative difference between the last two iterates as the stopping criteria. So the stopping criteria criterion is then if xr plus 1 minus xr, absolute value of this, is small compared to the last approximate. So if this is small enough, so if this is small enough, usually we take 10 to the power of minus 10 or something like that. Some really small number is small enough, we stop. So this is a tangent method. So bear in mind that we don't have any guarantee that this tangent method will converge. We have to know a little bit about our function to choose appropriate approximate. So this approximate should be near enough to the actual zero, and the function should not be too steep around the actual zero. Yes, so in the chat, Nate says that if h derivative is smaller than 1 in the actual zero, then there exists an interval around which this this method really converge. Yeah, that is one of the criterion in which we know we will get convergence. So yeah, we will look at this theorem. So before I write this theorem, remark if we have, for example, such a function. So let's say that it's something like that, and then it's something like that. You see, if this is our function, and if we choose initial approximate to be here, then using this tangent method, we see that already the second iterate will be far away, and no convergence is set. No convergence is assured. So we started with here with x naught, and then already the first iterate went very far away, and now we don't know what's happening on the left hand side. We could either come back, or maybe our function could have new zeros around this point, or it might also diverge. So we don't know anything. So we would want that our that we choose our initial approximate somewhere enough near to our actual zero. So our actual zero is here alpha, and we would like that x naught is enough near to alpha. So the method could diverge. However, there is a good news. So there is one theorem which assures convergence exactly under the criterion Nate mentioned in chat. So the sequence xi converges on some interval around I around the actual solution around alpha if we have two conditions. First, f derivative of x is smaller than 1, and this is for all this should be true for all x in the interval I. And second, x naught, of course, the first approximate should be within this interval. And there is also some technical conditions, so we don't want that this derivative is 0, because if this derivative is 0, then we don't we cannot calculate the intersection of the tangent with the x-axis, because then it will be parallel. So if there is some interval I around alpha such that the derivative is smaller than 1 for all x's on this interval, and if x naught is, so if the initial approximate is within this interval, then the sequence will really converge, and it will converge to alpha. For example, if the function is continuous, it is enough that f derivative of alpha is smaller than 1 in the absolute value. This will already assure that there is an interval around alpha such that this first condition will be met. So if f derivative of alpha is smaller than 1, this means that such interval I, given in the theorem, really exists. However, it's difficult. It could be difficult to find it. So it might not be very easy to estimate the absolute value of the derivative for all points on some interval. But at least we know that it exists. And if we will choose our approximate, which is near enough the actual solution, then the Newton method will converge. So yeah, the good question is how I would be chosen. And one way to satisfy, one way to answer this is not to try to choose it, but try to run tangent method for different initial approximates.
So, one question.
Yes.
Intuitively, from the remark we did before,
Yeah.
shouldn't we want a derivative to be more than 1, like a steeper derivative?
So here, derivative is here the derivative of h. Yeah, you see our h. So we are not, this is our h. Yeah, this is a good question. So we have this h, we are searching for its 0. And so if h is smaller than 1, if derivative of h is 0, then it will go away. Yeah. Just a moment, what I did wrong here. So the derivative is smaller than 1. Mm-hmm. So let's look at the proof. Probably this will be visible from the proof. Yeah, it's a good question. I cannot answer from head. Maybe it will be seen from the proof what's wrong here. So let's look at the proof. Probably this case will be seen from the proof what's wrong. Okay, so we have our f, and this condition that 0 is the derivative of f is different than 0 in every point means that it is simple 0. So that alpha is a simple 0 of f. And what we do is to express f in its Taylor expansion, and we only use the first Taylor polynomial. So let's say that we have ith iterate xi, and then we express first Taylor polynomial of f in this point xi, and what we get, we would get here. So f of x is f of xi plus then here f derivative of xi times x minus xi. So this would be the first Taylor polynomial with degree 1. And then we know also from the Taylor series that the error here is f second derivative over 2 factorial in some point, which is in some point eta. And this eta is between x and xi. So this eta is between x and xi. So I will write here, not write interval from x to xi because we don't know if x is smaller or bigger than xi. So I will write eta on between x and xi, and times x minus xi squared. So this is Taylor expansion, and this is the error. We know this from analysis. But if we plug in alpha, which is the actual 0 of f in this expression, we get exactly what's written here. So 0 is f of alpha, and it is this right-hand side when we plugged in alpha instead of x's. Okay, so this is this line 7. Now we divide this 7 with derivative of xi. And what we get is 0 is f of xi over derivative of f in xi minus, and then in this second term, derivative of xi of f in xi disappears. So we get alpha minus xi plus, and then the second term divided by derivative of f in xi. And now what we do is we put xi on the left-hand side, and this quotient also on the left-hand side, and this alpha true 0 also on the left-hand side. What we see here is that, so from the definition of the Newton's method, yeah, xi plus 1 is just xi minus f of xi over f derivative of xi. So this is just the definition of the next iterate in our Newton's method. So this is then this parenthesis is xi plus 1. And alpha is the true 0, so it's alpha. And what remains is on the other side. So here it should be minus. So minus is missing here. Yeah. But it doesn't matter now. And now, now let's say that this is the difference between, so we write this as the error of the E plus first iterate approximate. So this is E I plus 1. And this alpha minus xi was EI. So this is the difference between the true zero and ith iterate. And we got this equation. So E plus first iterate is ith iterate squared times some, I mean, the difference between the 0 and the E plus first iterate is the difference between ith iterate and 0 squared times some constant. And now what we know about this constant, so this constant, we don't know what's eta. So this is, let's say, m, which depends on eta and xi. This is second derivative of eta over 2 times f derivative of xi. But so at the beginning, x naught was from the interval I. So xi is in the interval I. And this eta is between alpha and, so this eta also belongs to alpha and xi. So it's also from the interval I. And we can now estimate from above this m. So it's at most in the, if we, instead of numerator, if we take the maximum of the absolute value of the second derivative in the interval I, so it's smaller than maximum of the derivative of x, of the second derivative of x in the interval I, while in the numerator, while in the denominator, we will have the biggest value of this m if in the denominator we take the smallest possible value. So we take minimum of this denominator. So x in I of the derivative of f in the point x. And now what our condition says, that the derivative is not equal to 0 on this interval I. And since we are dealing with a continuous function, so if it's differentiable, then it must be continuous. So if you're dealing with a continuous function on some interval, then its minimum is attained. We know this from analysis. So we know that this is then smaller than, so in the numerator, it's some constant m1, and in the denominator, it's again some constant m2. So altogether is some constant. Okay. This is then some constant m tilde. And now if we take, so what we know, E I plus 1 is smaller or equal to some constant m1 over 2 times m2 times EI squared. And then we write m1 over 2 m2 times, and then we take one EI separately. and one EI. We leave one EI here. And if if we chose EI small enough, so if the initial approximate was near enough to the actual 0, then this term is smaller than 1/2. So if the initial interval was small enough, then E naught is smaller than 1/2 times M1 over 2 times M2. And then what does this mean? That EI plus 1 will be smaller or equal to 1/2 times EI. So we can do this inductive argument. So we started with E naught, and then E1 will be smaller than 1/2 E naught. In particular, this means that E1 will also lie in the interval I. We do the same calculation with E1 and get that E2. So E1 is what we conclude here is that E1 is smaller than E naught, 1/2 E naught. And then E2 is smaller than 1/2 E1, which is smaller than 1/2 squared E naught, and so on. So En is smaller than 1/2 to the power of n times E naught. So this means that it follows that in the limit, when n goes to infinity, En will go to 0. So we, in fact, got convergence. And let's look what we needed in this proof. So in this proof, we crucially needed that this minimum of the derivative is not 0. So we know that minimum is attained, and we crucially needed that this minimum is not 0. So this is in fact the condition, the crucial condition. So and this won't be 0 if f derivative of alpha will be different from 0. But yeah, for the other condition that the derivative should be smaller than 1, I actually don't see where we used it. So maybe this is a good point to do a break, and after break I will try to explain why we needed this condition that it's smaller than 1, that the derivative is smaller than 1.
Justin?
So we did, at the end of the second hour of today's lecture, we studied this Newton's method for one equation in one unknown. We derived the method geometrically, and then we write the theorem about the convergence. And yeah, we come to this problem with this first condition that derivative must be smaller than 1. Yeah, actually, on the picture we saw that we don't want the derivative is too small. So if the derivative is big, then the convergence is even quicker. So yeah, and I admit I screwed up here. So we don't need this upper bound here. So we only need lower bound here. So 0 is not equal to f derivative of x for all x on the interval I. And this was also clear from the proof. So please correct here, and thank you for the remark. Thank you, Igor, for the remark. And only why there was this one, maybe just the explanation why there was this one. So this, what's our method? So xr plus 1 is xr minus f of x over f derivative of x r. And if we define this function, the right-hand side as the function g, so g of x is x minus f of x over f derivative of x. And you see the zeros of f correspond to fixed values of g. So if f of alpha is 0, then g of alpha is alpha. So zeros of f correspond to fixed values of g. And we can see the tangent method as the iteration of g. So is the iteration of g. So xr plus 1 is just g of xr. And it's called, this is called Jacobi iteration. And the convergence of the Jacobi iteration is met if g derivative of x is smaller than 1 for all x on the interval I. So this condition is fulfilled for our function f. For example, if f derivative is not 0 in the interval I, then this g derivative will be smaller than 1. This is easily seen. Just take the derivative of this g, and yeah, you will see that if f derivative is not 0 on the interval I, then g derivative of x will be smaller than 1 for every x. So this is a short exercise, but this is the source of my mistake, so I apologize. Okay, this was the tangent method, and we have this stopping criteria. So usually we will work with functions which have simple zeros. So this condition that f derivative is different than 0 makes sense. Usually the zeros won't be multiple, especially when we are working with numerical mathematics. Even if the function has double zero, the computer won't give us two exactly the same zeros. Okay, this was tangent method. And now, how does this method generalize to higher ends? So generalization. To higher n and m. But we still want that n and m are the same. So now we have our h is a vector function of a vector variable. And it maps n tuples into n tuples, and we would like to find its zeros. And in the tangent method, what we did was choose h naught, and then in the second step, calculate x r plus 1 as xr minus, and now I will write this in this form, f derivative of xr, so h derivative in xr times, and then h of xr. And here we have inverse because h derivative was in the denominator. This was for one variable case. So what would we take instead of the derivative for a for a vector function of a vector variable? So we need to find a generalization of this. And of course also this -1. So 1 and 2. There are 2 points to be generalized. So do you have any suggestion what would it take for the derivative of h if we have a vector valued function in a vector variable? What would make sense? So if you remember, so this h is now, this is n tuple of functions. They are all dependent on n variables. And what we can do, so we can differentiate each of these functions, each of these component functions with respect to any of the unknowns. So we have n functions and n unknowns. And so we can differentiate h1 with respect to a1, with respect to a2, up to with respect to an. And this is what we can do for every coordinate function. And this is exactly what we do for the derivative. So the so-called derivative, or so let's say derivative of h, or also a Jacobi matrix of h in the point, we have to fix the point, in the point a in R to the power of n, is the following matrix. So D of h in the point A, or also J of h in the point A. So it is the same thing. So this would stand for the, this notation would stand for the derivative, and this notation would stand for the Jacobi matrix. So, but this is the same thing. So this is a matrix where in the first row we take derivatives with respect to the first variable, to the first function. So h1, we take the derivative of h1 with respect to a1 and calculate in the point A. And then in the second column, we take the derivative with respect to a2 in the point A, and so on. So in the first row, we have derivatives, all possible partial derivatives of h1 with respect to all variables, and so on. So mth row corresponds to mth function and coordinate function, and then we take all possible derivatives. So another way to say what's the Jacobi matrix is to say that it's the matrix where the rows are gradients of the coordinate functions. So the first row is gradient of the function h1, h1, yeah, and then the second row is gradient of the function h2, and so on. And then the last is gradient of hn. And if you recall, I said that in the algorithm we would like, we have h of a, and we want to do a linear approximation. So linear approximation should be a linear function. So if this h is a function from r to the power of n into r power of n, so this linear function should again be a function from r to the power of n into r to the power of n. And it makes sense that, so if it's linear, then it's of this form L of a in the point L of a in some point is ax plus b. And there are two conditions which make sense, so that L of a in the point A is equal to h of a. So in our solution, so our solution is alpha. And the derivative of this linear function in the point alpha is the derivative of h in the point alpha, so this dh. So these are two conditions which generalize what we had for tangent method. So in the tangent method, we wanted that in the point the function value and the function value, so h of alpha and the linear approximation in alpha are the same, and also the derivatives are the same. These were two conditions. And again, what we did in the tangent method was that L was exactly of this form, L of a x. This was so h of alpha plus, and then we had here something. This was exactly the derivative times x minus alpha. Yeah, and if when we plug in x alpha in this equation, we should get exactly dh of alpha. So this is then the generalization. This is then our linear approximation.
Is alpha here a vector?
Yes. In fact, this should be here. This alpha. So we are doing this algorithm. In every point, we do another approximation. So I wanted this index in L is in fact the current point where we calculate this approximation. So these indexes should be alphas. Alpha is tuple from r to the power of n. Yeah. And these conditions are really satisfied by construction. You can simply see that what's the by the definition above. By the definition above, you can see that so the Jacobian matrix is the matrix of gradients of the coordinate functions. And let's do this calculation. In fact, I jumped over this calculation. So example, let's say that L is a linear function, linear vector function of this form. L of x is ax plus b. And let's calculate the Jacobian d of L in the point A. Let's calculate this Jacobian. So in the long form, this is just a11 x1 plus a12 x2 plus so on plus a1 n xn plus b1, and the same for the other rows. A n1 x1 plus a n2 x2 plus so on plus a n n xn plus bn. This is our function L. And now we are calculating the Jacobian dl in the point, let's say, A, alpha, let's say alpha 1 up to alpha n. So this is a matrix. It has the same number of rows as L and the same number of columns as are the number of variables. So here we have n variables and n unknowns and n rows. So it will have n rows and n columns. And first we calculate the derivative of the first function with respect to x1 and get just a11. And then in the second column, we calculate the derivative of this with respect to x2, and we get a12. And so on. So we calculate the derivatives with respect to all the variables, and we get a1n. And you see the same pattern for all rows. an1 plus an2. I mean, not plus, but an1 in the first column, an2 in the second column, and so on, ann in the last column. So the derivative of a linear function is exactly what we expect. So it's this matrix A. And this is what I've used here. So I formed this L of alpha. And this matrix derivative of the function h was the matrix coefficient of at x. So if we take the derivative of L, we take exactly this dh. But if we plug in alpha for x, then the second part disappears and h of alpha remains. So in our algorithm, generalization of the Newton's method, what we do is we already know what to do, what to take instead of this derivative. So we take the Jacobian of h, And since this is n by n matrix, we can really calculate its inverse. So this -1 is inverse. And this is the Jacobian matrix. So Newton's method. N is equal to m is bigger than 1. H is a vector valued function of a vector variable. Choose x naught. This is a vector from r to the power of n. And then calculate xr plus 1 is equal to xr minus. And here we have derivative of h in xr. So this derivative, this Jacobian matrix, must be calculated in every step. So it changes from step to step. And then we take inverse. And calculate with the value of x, xr. So this is a vector. So this is a matrix. And this is a vector. However, inverses are very expensive to calculate. And this second step can be done in a more efficient way. So inverse is expensive to calculate. So what we rather do is multiply this second equation by the matrix DH in XR. And what we get here is D of H in XR, so Jacobian matrix times XR plus 1 is equal to Jacobian matrix times vector XR minus, and so here we just kill this inverse. So what remains is H. And now we put this on the left-hand side and we get D of H XR on the vector XR plus 1 minus XR is minus H of XR. However, we don't know X of R plus 1, but we can write this as a step. So we know XR, so this is step in XR. And we solve this system. And it's better to solve such a system. This is now square system. We solve this system with LU decomposition. We didn't study LU decomposition, but in Matlab, LU decomposition is done in this way, dH of XR, then minus H of XR. So this is Matlab notation for solving this system by the method of LU decomposition. It's just Gaussian elimination in a more stable way. This is not the domain of mathematical modeling, but more of numerical mathematics. And we get this delta XR. And then how to get XR plus 1. So XR plus 1 minus XR, this is by definition delta XR. So we know XR from the previous step. We calculated delta XR, and hence we have XR plus 1 is XR plus this step delta XR. And this is how we do Newton method in a more stable way. So we choose, in the first step, we choose vector x naught. Then we solve this system, Jacobian matrix in XR times some vector is minus the value of H in XR. get this vector and then calculate the next iterate in this way, xr plus this step. Is there maybe some questions? Okay, before we go on, I would like to show you how to use this method in Octave. It's quite simple. Let's look in this example we had in the first hour today. So let's recall this example. So we had this microwave positioned at location AB. We know that the radiation is modeled by this function, and we measured the signal of the microwave in 3 different locations, and we got this system of 3 equations in 3 unknowns. Unknowns are alpha, A, and B. And we would like to find a solution. And so we would like to use Newton's method. First, if you recall, we said that we have to put those values from the right-hand side on the left side so that we have zeros. So our function is then, our functions are then what remains. So the first coordinate, the first row will be, the first function will be the G1, then the second will be G2, and the third will be G3. So to apply Newton's method, what we need, we will need a derivative of this function. So we now our H is then G1, G2, G3. And to apply Newton's method, we need this Jacobian matrix. So D of H in every point. So alpha A, B. So the first row is derivative of G1 in alpha. What is this? So let's take the derivative. So here we have this 0.27 is not important when taking the derivative. So only this first part is important. So let's do the calculation. So when we take the derivative of this function with respect to alpha, we get 1 over 1 plus square root of a squared plus b squared. So this is the partial derivative with respect to the first variable. And then we take the derivative with respect to the second variable. So alpha is just the parameter. And then we have, this is a composite function. So you have to remember how to calculate the derivative of the composite functions. So we have, I will do this calculation here because all the others will be the same. So we take the derivative, the partial derivative of 1 over 1 plus a squared plus b squared. So the partial derivative with respect to a of this function. So it's in fact 1 plus square root of y squared plus b squared to the power of minus 2, because this is 1 plus square root of a squared plus b squared to the power of minus 1. So we have to first the outer take the derivative of the outer function. We get minus 1 over this function squared. And then we have to take the derivative of what's in the denominator. So it's the derivative of the square root of a squared plus b squared. So it's 1/2 times, so the derivative of square root is 1 over square root. And then we have to also take the derivative of the function inside the square root with respect to a. So this is 2a. And yeah, this is what we get. This is what we get here. I won't even rewrite this. So this 1/2 and 2 cancels out. And very similarly, so in the third column, derivative with respect to b of this same function. Yeah, I had here alpha, also alpha. So 1 plus square root of a squared plus b squared. So this is symmetric in a and b, so it will be completely the same, only that instead of a, we'll have b. And similarly for the second and third row. So in the second row, I take the derivatives of the second function with respect to all three variables. And in the third row, the derivative with respect to the third function. And I built a Jacobian matrix of size 3 by 3. And then I can use the Newton's method. And let's look at the example. Let's look at the calculation in Matlab. So I have this here, Newton for systems. You see, this is the script. So we have f is our function. Jacobi of f is our matrix. X naught is the initial approximation. And then delta is our stopping criterion. This is when the relative error is smaller than some small number, 10 to the power of minus 10. Or if we don't put it as an argument of the function, then it's taken to be epsilon. And we can also limit the number of steps of this method until convergence. And if, again, we don't put this as a parameter, then it's 50. And what does this method do? So here we check the stopping criteria. If the relative error is smaller than delta, we stop. If it's bigger than delta, then we do another repetition of Newton's method. And the second condition is that we haven't reached the maximum number of allowed steps. And what we do here is we calculate this delta. This was solving the system. Jacobian matrix of times delta is the right-hand minus right-hand side. So this is what we do here. And a new approximation is just the old one plus this step. And we print everything out. So the way to define those f and the Jacobian matrix is as an inline function. The example is here. So we have we have this command inline, and then we put parentheses, and then we have here. So it's a vector of 2 coordinates, and in the coordinates we have functions. So and x1 is x, and then x2 is y. So this is a function in 2 variables. So we have to, our x is in fact a vector. So that's why we have x1, x2, x3 for the variables. Okay, and our example. Yeah, this is our example. So this is our function f as an inline function. This is for this radiation. You see x1 is alpha, x2 is a, and x3 is b. And so this is first coordinate function, then the second coordinate function, and the third one. And here I have the Jacobian matrix. You see that it's quite long. It has in the first row I have the derivative with respect to the first function, then the derivatives with respect to the second function, and to the third I have to calculate this in advance. And then I call Newton system. So f will be our function. Jacobian of f will be this Jacobian function, and this is initial approximation. So I put 1.1, 1.1, 1.1. So alpha, beta, alpha A and B. I just put 1.1 for each of them. And I will run this example. So you see, this is after the first step. This is alpha A, B, and relative error, which is 10 to the power of -1, so quite big. And we are repeating this procedure. And after 37 steps, we converge to a solution. So this is alpha, this is A, this is B, and this is relative error. So it's 10 to the power of -6, so it's smaller than epsilon, which means that we stop iteration. So this is the solution then for this microwave problem. Okay. This is all for today. Next time, so what we will do next time is to generalize this to Gauss-Newton method, where we won't have a function h from r to the power of n to r to the power of n, but n and m will be different. For this case, the only difference will be that Jacobian matrix will stay the same. So still we can take derivatives of each of the coordinate functions with respect to every variable, but we cannot calculate here inverses. But we already know what's the generalization of the inverse. It's, for example, Moore-Penrose inverse. So generalizing Newton's method to non-rectangular non-linear models is Gauss-Newton method, where in the algorithm, instead of taking inverses, we take Moore-Penrose inverses.